Hey everybody, we're on lesson 4 today, talking about piecewise functions. We're going to graph them, write equations for piecewise functions, evaluate them, and then do some real world applications. So a piecewise function, we said in the last lesson, would cause jumps in our graph, where one function jumps to another function. This is the format or the standard notation for writing piecewise functions. We're going to have an equation here, and then we're going to have this subdomain. This part is called the subdomain of a piecewise function. And you can have 2 or 3 or more equations with supporting subdomains. Our most famous piecewise function is that of absolute value. So if you think about absolute value, we can define absolute value this way. The absolute value of a number x is going to be just the number itself if x is 0 or positive. But it's going to be the opposite of x. That's not negative x, that's the opposite of x if x is a negative value. Okay, so if I graphed the first equation, y equals x, we know that's a straight line that goes through the origin, and every y and x are the same value. But we don't draw this piece of the graph because they've stopped us at 0. We start at 0 and go to the right for only positive values. The other piece, or the other branch, using the subdomain for all negative values, is y equals negative x, which is the line that goes in the opposite direction, like such. So we're opened at 0 on this branch, and we're closed at 0 on this branch, which makes that function a continuous function. There's no break in the graph. So yes, the function is continuous. The domain of the function is all reals, but the range of the function starts at 0, includes 0, and then is bounded upward on both extremes, to the right and to the left. Where's the function increasing? Well, the function increases from 0 to infinity, and then the function decreases from negative infinity to 0. So just practicing that analyzing. Here's 2 more famous piecewise functions. You may or may not have seen them. The ceiling function is represented by this type of notation, and it means we want the least integer greater than or equal to x. So if you think about that from a perspective of starting at 1 and going to 2, and we want the function value on the ceiling function at 1.5. Whoop, I'm drawing the greatest integer function. Oh, okay. Fix my notation here. So the ceiling function at 1.5, if you think about it this way, I'm at 1.5 and I want the smallest integer greater than my value. So greater than my value is to go up. That's the ceiling function. I want to step it up. So when I think about 1.5, then I want that graph right there. Oh, I want this graph right here. So when I'm at 1.5, when my x value is at 1.5, I want to step up to 2. And then if you follow that logic, you can sketch the graph between 3 and -3 this way. I'm always stepping up. Stepping up. That's called the ceiling function. And they asked us to graph between -3 and +3. So I'm starting at -3 and stopping at +3. I really should probably have some open parentheses here. This should more likely be open parentheses. Stopping at -3. The floor function would be the same thing, only backwards. So think about it this way. We want to step down on the floor function. If we're at 1.5, we're looking at the function value on the floor function at 1.5. And I want to go get the smallest integer. This should say less than. I'll have to change my slides. That is less than or equal to x. So in this case, the floor function would have a step down back to 1 because we want the lower end. So where's 1.5? 1.5 is right in here, and I want to step down to 1. So we can step down all the way back to -3 and all the way up to +3. So again, I'll make these corrections for your teacher so that the slides are correct. This would be 3 open, and this would be -3 closed. So the function values are correct, and we're stepping up for ceiling and down for the floor function. We can evaluate piecewise functions in this example by finding the expression or the equation for the domain that we're given. In this case, we want the f of 12, and 12 lives in this subdomain. So when x is 12, we would use 5 minus 1/2 times our x value of 12, and that looks like 5 minus 6, so the f of 12 would be -1. In this case, the f of 2 is the middle expression or equation, y equals 2. So on our subdomain, the f of 2 is 2 when the x value is 2. On part C, the f of -5 would fit this subdomain, and the function would be -2 times the absolute value of -5 plus 1. So I'm just substituting my x value into the equation. That looks like the absolute value of -4. So that gives me a +4 times a -2. The f of -5 would be -8. And then where does 0 fit in? 0 fits in to the same absolute value. So -2 times the absolute value of 0 plus 1, or -2. So we can evaluate piecewise functions simply by paying attention to which equation fits the subdomain for the given x values in our expression. Here's one for you to try. You can turn off the video and work for yourself, and then come back to check that your work matches my work. On part A, I used the top equation, 3x minus 7, and got the f of 6 is 11. On the B portion, I used the bottom expression, -3 is squared minus 1, so the f of -3 is +8. Hopefully you got those same answers. In example 4, we're going to work backwards now. I'm giving you the graph and asking you to find each expression and the subdomain. So starting here on the left, I see that the equation has a y-intercept of 5, and it looks like the slope is -1/2. So that first expression or first equation is -1/2 x plus 5. There's an open circle here at 2. So the subdomain would be for x less than 2. The middle piece is just a y equals 3 graph, and y equals 3 is closed at 2 and open at 5. So our subdomain would be 2 less than or equal to 5, and then x is less than 5. Now this one, you might want to follow backwards and find out the slope is 1, where would the y-intercept be? So that would be one way to figure this out. Looks like our y-intercept would be at 7, and the slope is -1. The step is down 1, right 1. So our equation for that third piece is 7 minus x, or -x plus 7, whichever way you want to write it. We're closed at 5, so the x values would be greater than or equal to 5 on our subdomain. And you could either write your equation this way or this way. That's up to you. Part B is for you to try. So turn the video off and then come back and check to see that you have my results. And I end up with x squared minus 3 for all the values less than or equal to 2. The middle piece is the open interval from 2 to 5, and the third piece is x minus 3 for all the values greater than or equal to 5. So that's pretty easy. In example 5, we're going to graph each piece ourselves. Now this might take a little bit of work. I know this is an upside down parabola. The HK value, or vertex of the parabola, is at -4, +3. And if you substitute -1 right here for your x value and complete that, you're going to get -1, -1.5. So we're going to have that value right there. We've got a vertex at -4, 3, and it's an upside down parabola that I've pre-drawn, and it should look something like that. The middle piece, using that same logic, it's got a slope of 3 on the absolute value, and the HK value, our vertex, is going to be at 2, -4. On each side of the absolute value, we're going to see a slope of 3 or a slope of -3, and our interval is from -1 to 4. So I'm just following the slope, 3 up, 1 right, 3 up, 1 right, and repeating that toward the left. 3 up, 1 left, 3 up, 1 left, and stopping at -1 and +4 with open circles there. Then the third branch, the vertex, or the starting place in this case, since it's a cubic, it's going to be serpentine, and we're going to start at the point 6, 2. And you know, when the A value is 1, we would have a point at 7, 3, and 5, 1, and it's going to curve around there, low on the left and high on the right. And then we could evaluate at 4. So we would know the value at 4 by substituting 4 here. That's -8 plus 2. So at 4, the y value is -6, and it's going to be closed up there, but it's going to go infinitely high on the right. So we have this sort of serpentine graph in that area. So it just takes a little bit of thinking and planning and paying attention to the subdomains so that you get your intervals correct with the jump discontinuities. There's a closed at -1, and then open on the absolute value, both ends, and closed at +4 on the cubic, and open forever on the right end. Okay, here's another skill. We're talking about using number lines. Oftentimes in Algebra 2, we didn't really use number lines a lot, but we're going to practice those skills in pre-calc because they come in handy for later on in calculus, finding behavior on derivatives and analyzing functions. So using this absolute value graph that we looked at in an earlier lesson, we're going to develop a technique that'll help us get a strategy for not only practice use of number lines and behavior, but also for converting an absolute value graph into a piecewise function. So what we want to do is we want to be able to find the zeros of that x plus 2 argument and that x minus 1 argument. This was our function, and it was called g. So g was this, which means we've got a 0 at negative 2 and another 0 at positive 1. So we want to use those zeros to divide up the number line, and then we want to pick some values. Let's say negative 4, 0, and 2. We want to pick a value in this region, pick a value between negative 2 and 1, and pick a value greater than 1. I could have picked negative 3, that's fine, but 4 will work too. So all we got to do is think about the behavior. So I'm going to think about it this way. In fact, I need another piece of paper, and I'm going to turn my view to dual page mode so we can do this computing together. So let's say we have x is, get my blue pencil, x plus 2, and then x minus 1 minus 2. And I'm trying the number in my head for negative 4. So if we put a negative 4 here, or any negative number for that matter, this is going to turn out to be a negative answer. And if we put negative 4 in the second piece, let's see, I need to move it over. I didn't put my plus sign in there. Rewrite that. So plus x minus 1 minus 2. You notice I'm not using the absolute value bars because I just want to test the value at that particular test number. So if we put a negative 4 in here, that too would be negative. So simplifying this expression with our result of that test, we would end up with negative x minus 2 minus x plus 1 minus 2. Combining like terms, we end up with negative 2x minus 3. So this is the piece of our equation in the subdomain for all the x's less than or equal to negative 2. So that's one piece of our piecewise function. Next, we're moving to the middle section when x is 0. So we want to do that same process again when x is 0. Testing 0 into the equation without the absolute value bars. So if I test a 0 here, I end up with a positive number. And if we test 0 here, we end up with a negative number. So distributing those signs to our expressions, we have an x plus 2 minus x plus 1 minus 2. And to simplify all of that, the x's are gone. 2 plus 1 is 3, and 3 minus 2 is 1. So our middle function is y equals 1, and it fits in the interval from negative 2 to positive 1. So negative 2 to positive 1. Now I'm making this executive decision. If I close up the graph here, I can open it here, and I can either choose to leave it open or closed. It doesn't really matter. Then this piece, x equals 2, will be our last test area. And I want to test a positive 2 inside of my expression without the absolute value bars. And if we substitute a 2 in here, that result would be positive. If we substitute a 2 into this argument, that would also be positive. Collecting like terms, we've got 2x and then 2 minus 1 minus 2. So our expression or equation for that branch or that interval is going to be 2x minus 1, and that's going to work for everything bigger than, let's see, we opened this, so I'll say greater than or equal to 1. So this branch, and this branch are going to make up our piecewise function. And you've got a piece of graph paper. So we want to rewrite that. The g of x, this is our piecewise function. The g of x is going to be negative 2x minus 3, negative 2x minus 3 for all the values in our subdomain less than or equal to negative 2. Then they're going to be y equals 1 for the subdomain between negative 2 and positive 1. And then lastly, 2x minus 1 is the equation for all the values greater than or equal to 1. Okay, and we want to look at the whole page now. So 2x minus 3 in a negative direction would be, let's see, 2x minus 3 is going to go off that way, but we want that to only work starting at negative 2. So if you follow that pattern, 2 down, 2 down, it would start right there. And like I said, I could close it up there. And then y equals 1 is going to be a constant function. And it's got an open circle on both ends. So open here, but this one closes. And this one's open. That's not a very good open, is it? But you get the idea. And then the last piece was 2x minus 1. So 2x minus 1 would do the same thing. We would start down here at negative 1, but we wouldn't draw this one. Rise 2, run 1, and close that up there and draw that graph. So we have the piecewise function. See if I can group it and shrink it up so it's nice and pretty next to our graph. Okay, so the next one is one for you to try. If you'd like to turn the video off and work that out for yourself, see if you've got a handle on this skill, and then come back to meet me to see if we have the same results. Okay, this one I ended up with 3 zeros, 1 0 at negative 2, and I'm sorry, 1 0 at negative 1, and 1 0 at positive 1. And I needed to test 3 numbers. So those were my 2 zeros for this argument and this argument. I'm going to test, I tested negative 2 into the expression x plus 1 plus 2 times x minus 1, and my results were negative and negative. So distributing that, we got negative x minus 1 minus 2x plus 2, and my function was negative 3x plus 1 on that subdomain. So negative 3x plus 1 ended up being that graph. And the subdomain was for x less than or equal to negative 1. So this was the first piece. If I tested the next interval, I could use 0 for my second interval in between negative 1 and 0. Testing in that same expression, x plus 1 plus 2 times the quantity x minus 1 gave us a positive here and a negative here. And our final result was going to be negative x plus 3. Collecting like terms. And that would be on the subdomain between negative 1 and positive 1. So we've got negative x plus 3 on that second piece. And that would look like that portion. And then this is going to be our last one. If we test x equals 2, since 2 is bigger than 1, We can test 2 into the expression x plus 1 plus the quantity 2 times x minus 1. In both cases, if you try 2 into that expression and this expression, they're going to be positive. So distributing a positive and collecting like terms, we get 3x minus 1 for the third subdomain, and that's everything greater than or equal to 1. So to write the piecewise function for f of x would look like 3 pieces, negative 3x plus 1 for everything less than or equal to negative 1, negative x plus 3 for the open interval between negative 1 and positive 1, and then 3x minus 1 for all the values greater than or equal to 1. I hope you got the same results I did. We'll finish the lesson with 2 practical applications. This first one, in the imaginary world of Leibniz, if a person is filing single, not married, they're paying taxes based on this table. And we want to be able to write a piecewise function for the taxes, giving the tax owed by a person whose taxable income is less than 125,000, since that's our maximum here. So let me turn on that dual page again so we can see both pages. And then thinking about this, if you've got 15% for less than $30,000, then that's going to be our first piece of the piecewise function. %, 0.15x, and that works for anybody earning money greater than 0. You wouldn't pay anything if you didn't make anything. And up to $30,000. Now for the middle section, we're going to pay $45,000 plus 20%. So $4,500, I'm sorry, $4,500 plus 20% of everything you earn between $30,000. So that's open there, and up to, let's see, $65,000. And then if you make, well, this one would be open, wouldn't it? Okay, and then if you make 65,000 or more, up to 125,000, less than 125,000. I keep filling that in with equals. That would be 11,500 plus 24% of your income. So our taxable tax rate, this is a mess, is going to be these 3 equations with these 3 subdomains. Let's see how we can group this up. Make it a little bit smaller. Oh, no. I don't know if I can make it smaller. So it fits on the page better. Well, anyway, you get my picture. And then we want to evaluate that for someone that made $68,750. So that looks like we're in this middle region here. So we want to evaluate there. Okay, I got that looking a little neater. Now we're going to evaluate for $68,750. So we're looking for how much money he makes or she makes. The tax on $68,750. So we'd have this last region here, 68,000 would be $11,500 plus 24% of the excess, right? So the excess is going to be 68, that'd be $3,750. $3,750. So 24%. 24% of 3,750 is an extra $900. So 11,500 plus an additional 900 means a single person making $68,750 on planet Leibniz is, in the land of Leibniz, is going to pay $12,400 in taxes for that year. Wonder how that compares to the US. So I live in Orlando, Florida, and it's really hot in August. And in August, I took this off of our electric bills from 2017. They charge $8 plus 10 cents for every kilowatt hour. And we want to know what the charge is for using 920 kilowatt hours. So this is the charge for the first 1,000 kilowatt hours. That means for 900 kilowatt hours, you would pay $8 for an initial amount, and then 920 kilowatt hours at 10 cents a piece. So cents, we're going to move that decimal over 2 places, and that would be 0.10143. So calculating that, $8 plus 0.10143 times 920 hours of usage, we would pay $101.32. You know they're going to round up and take that penny. Okay, what's that charge? And what would be the charge for 1,500 kilowatt hours? So you see the next rate up is 12.143 cents on part B. So we're going to pay $8 for initial. And for the first 1,000 kilowatt hours, we're paying the 10 cents for 1,000, which is going to give us 8 plus 101.43. And then we got 500 extra kilowatt hours for the 12 cents for that. And I believe that's about $60. 0.12143 times 500. So $60.72. The total would be $170.15 if you used 1,500 kilowatt hours. If C is the monthly charge for X kilowatt hours, can we write a piecewise function to describe that charge? Well, we know C of X is $8 plus 10 cents for every hour between 0 and 1,000 kilowatt hours. But if we're more than 1,000 kilowatt hours, then we're going to pay a second charge, a second interval. We'll call this one C sub 1. It's going to be $8 plus, if we put 1,000 in here, that was 101.43, and then we're going to pay 12.143 for every hour after 1,000 are used. So I'm going to do X minus 1,000 to make that be over 1,000. So doing that math, we've got 12143x. Whoop, I missed a 3. 12143x minus 12 for all the hours after 1,000. So putting that together, our piecewise function would be the c of x is 8 plus 10 cents for every hour from 0 to 1,000, and 12143x minus 12 for every hour, kilowatt hour over 1,000 kilowatt hours. So that's pretty much it for this lesson. We have 4 more lessons to go in the unit. See you next time.